SLEMI Automated Compiler Bug Finding for Simulink. When designing complex cyber-physical systems, engineers design graphical models to simulate them in commercial tools like Simulink and even generate code to deploy in target hardware. Now, a bug in the toolchain can introduce further bugs in the artifacts they automatically generate. And we don't want safety-critical systems to fail due to compiler bugs. So we need automated tools to test Simulink. State-of-the-art tool SLForge automatically generates valid Simulink models in order to test Simulink. It's inefficient, however, since generating a valid Simulink model from scratch is very slow. Our tool SLEMI is first of all fast, since it just introduces small changes to an existing Simulink model instead of trying to generate a whole model from scratch. It also found more bugs than SLForge. We gave the two tools similar resources. When SLForge found 2 bugs, whereas SLEMI found 10 bugs in various Simulink versions. We use EMI, short for Equivalence Modulo input, which takes a Simulink model known as SID and automatically create a mutant such that they are functionally equivalent when we compile and simulate them in Simulink for some input I common to both. SLEMI has 3 independent components. First, a framework to run experiments on Simulink models, such as pre-processing the seed models to improve overall runtime. Next, we create EMI-based mutants from these seeds. Lastly, high-performance differential testing to compare the mutants with their seeds. Any difference we find is likely indicator of a compiler bug. All of our tools are open source and require MATLAB version 2018A or newer. We start with the experiment framework, which scans for seeds in a distributed file system or in a local file system to pre-process them in parallel and caches intermediate results, such as coverage, data type, and sample time of every block in a seed. Using this information, we then perform several one-time base mutations per seed, which further improves overall runtime. Our EMI component then consumes this cache and generates multiple mutants per seed in parallel. Lastly, our differential testing component compiles, runs, and compares mutants with their seeds again in parallel. To launch a tool, use command line or MATLAB's graphical user interface. For example, here the experiment framework. In Explore mode, it scans a file system for seed models. It can also directly consume SLForge's generated models. We have many options to filter out undesired models. For example, here we only select those which were generated after a particular date. We can process models in parallel and merge results from all of them once the experiment completes. Simply run the tool again to merge. We can limit the number of seeds and only process a subset. Now demonstrating EMI and the differential testing component. In each of the experiments, we will generate 100 mutants in parallel, and each of the experiments will be random. Experiments will stop as soon as we find any bug. It will automatically invoke differential testing, which will not only compare mutants with their seeds, but also run each model in optimization on and off and normal and acceleration simulation modes. In debug mode, we highlight the changes made by a mutation operation in graphical user interface. We can debug all blocks in a seed, or a particular child model in the seed, or even in block level granularity by specifying its name. Quick demo of the debug mode. The highlighted block will be deleted when user presses any key. Next, we add a new saturation block and connect it with the predecessor and the successor of the block we have just deleted. For likely bugs, we can automatically load the mutant and its seed in GUI. We can choose to only generate mutants from specific seeds writing rich queries, and can choose the percentage of zombie and live blocks to mutate. All of our base, live, and zombie mutations are implemented as MATLAB functions. Base mutations are automatically detected and run during pre-processing. Similarly, live mutations are also implemented as MATLAB functions. Here, each mutation strategy is equally likely to be selected, except the first one, which will never get selected. We are thankful to our mentors at MathWorks. Thanks for watching. Please fork at GitHub and contribute.